you for the introduction, for the invitation. I'm sorry I'm not there physically. Okay, so I'll be talking about electrocatalysis, electrocatalytic interfaces exposed to a liquid and how they might be changing in reaction conditions, and how that's important for understanding of the mechanisms and future pursuits and design of efficient electrocatalysts. So usual view of theories on a catalytic interface would look something like this. You know, there are millions of papers in the literature that look somewhat like this, where the view is as follows. You have some metal surface which stays put, and indeed we learn, say in high school, that catalyst is something that stays unchanged during the reaction. So you have a catalyst that doesn't go anywhere, say surface 111 surface of a metal. Some molecules come, they break bonds, they form new bonds, and voila, you have a product. And the common wisdom is that for the key reaction intermediates that determine the rate, you don't want the affinity to the surface to be too high or too low. And if you have this just right affinity, then you have a good catalyst. And it seems like problem is solved, except it looks to the almost boring. I want to convince you that it's not boring at all, and that this picture is grossly incorrect in some cases at least. So I'll show you a prime example of what I call fluxionality. People call fluxionality in the field, which is something, so in an interface that looks kind of like this. So we have small clusters, say containing fixed number of metal atoms, in this case copper. And this is from an actual simulation. So you have 4 copper atoms, varying amount of oxygen in the cluster, and depending on the isomer you're looking, you will have different number of oxygens, and also they're colored differently because they have different reactivity, and they're sitting on amorphous alumina, which of course presents a variety of sites on which these clusters could be landing. This comes from simulations of oxidative dehydrogenation of propane catalyzed by these clusters. What I'm advertising here is that it's not one fixed structure of this catalytic cluster, but a variety of them. And the reason for this is that potential energy surfaces or free energy surfaces of such tiny clusters are usually very architectural. There are many minima. And while the usual focus has been on the most stable structure, the global minimum, in reality, we are not in spectroscopic conditions, not in ion beam, we're at catalytic temperatures, and so we have a variety of these minima that are, of course, accessible thermodynamically and kinetically. And so we cannot really think of the catalyst as just one put structure like here, but instead it's a collection of many. And furthermore, they easily interconvert. They isomerize one into another with varying barriers. Some of them are low and some of them are high. And so we should be seeing this interface as an ensemble of many things, not one. And we have to be thinking of it in a statistical, mechanical view, where it's an ensemble that's catalytic. And furthermore, what we've seen over the recent years is that often the less stable species in this ensemble may be driving all the catalytic turnovers. It's actually very instinctive. Something that's more stable should not be very reactive, and something that's less stable should be more reactive. So often global minimum is actually a catalytically dead species. And it's something that's rare and comes and goes during the reaction at low percentage of the population, maybe doing the catalysis. Whereas, by the way, Parando spectroscopy would be looking predominantly at the global minimum because an ensemble averaged signal usually. So this is a paradigm that we brought to the field and we've been developing for the past little bit. There are some reviews that we wrote on how big and small can these ensembles be? It depends on the system. So I'm playing so far with surface supported clusters, but at the end I'll show you something that's characteristic of a bulk interface too. So here, for example, if we look at platinum 8 cluster as opposed to an alpha aluminum, and you study them in simulations in conditions of dehydrogenation, so it's high temperature and low partial pressure of hydrogen, versus hydrogenation, where you have a low temperature and high partial pressure of hydrogen, you will see drastically different picture. So on the left, you see all sorts of isomers. You see there, maybe it's hard to see, but they're different in structure, hydrogen coverage and hydrogen placement, as well as where they sit on the support. And all of them are there in reaction conditions. And these guys looked into just one structure, very much hydrogen covered, unusual shape, far from globular, and it's only one isomer that we can see as accessible by simple Boltzmann statistics. In electrocatalysis, things start getting a little bit more intricate. Here, still within thermodynamic equilibrium picture, we look at platinum 5 on support on graphite. we in addition to all the species that are present and can bind to the cluster and change the cluster shape, we also have electrochemical potential. So once we start charging the electrode and depart from the computational hydrogen electrode model, say, we start seeing that the species, all of them again are present, they can also interconvert as a function of the applied voltage. So for instance, all these minima, they can be populated to a certain degree, but as a function of the potential, we see their intercrossings, okay? So one isomer can be predominant at one window of the potential, they can mix in another, and so on. So the picture is very complicated here. And in addition, what I'll show you is that the kinetics start playing a very non-trivial role because temperatures are low, the room temperature, and so we cannot really, so this is complicated enough. It's something that hasn't been really, interfaces have not been modeled like this traditionally, and it's of course very labor intensive, but when kinetics starts playing an additional role, that complicates the picture even further. But overall, what this paradigm leads to is that we cannot say there's one active site, there are many. We cannot say there's one mechanism, there are many, and collectively as a swarm of different mechanisms, they contribute to experimentally observable activity, selectivity, spectral signatures, stability, and so on. Okay. Technically, how do we do this? In case there are theorists and audience who want to see, we have a grand canonical sampling strategy where we simulate the structure of the interface simultaneously with their coverage with relevant adsorbates. And it's done under relevant temperatures, pressures, or chemical potential of the adsorbates that may be binding. And in case of electrocatalysis, also electrochemical potential. And it's done in this case, it's a genetic algorithm scheme. It's well established since about 20 years ago, but it's done grand canonically. So because this is so expensive computationally, sometimes machine learned potentials are important. And they can really help, but the accuracy has been a problem, at least in our hands, particularly for very small clusters. It may work better for larger systems where chemical bonding doesn't change so dramatically from just a small change in the geometry, but for small clusters, it's very difficult to train something reliable. We have some, but usually we try to stay away from them. And then kinetic effects create nanoids. I'll show you just in a second. So why is it important to do this sampling grand canonically? Just a quick example. You don't need to go into the chemistry of what's going on here, but I'm showing you some phase diagram of the interface that's a hexagonal boron nitride, and we look at the edge present in again oxidative dehydrogenation conditions. And this is just a sampling illustration. We sample through structure and the content of boron, oxygen, and hydrogen at this interface all at the same time. And this is my sampling trajectory from start to finish. You see it's quite direct. We don't sample everywhere in this box, so we save on time quite a bit. And also we really improve the quality of sampling. So if we go randomly, for example, we will have some distribution of cluster energy or interfacial energies like this. And if we sample grand canonically, we're more direct and we're closer to lower energy regime. Okay. And also, again, just one technical slide for how we simulate the electrified interface. When we want to charge the interface, we assume a capacitor model. We literally add and remove electrons from the interface. It's done in a symmetric slab to not charge just one phase. And then the electrolyte is treated implicitly through Postman-Boltzmann solver, which creates non-uniform background charge distribution, mimicking the double layer. Okay, it's not perfect. Explicit electrolyte would be nice, but we cannot do it simultaneously with charging the electrode for technical reasons. And also, we're really focusing on sampling of the electrode structure rather than sampling of the solvent at the moment. So, but of course, ideally, we would want to do all of this. This work is done collaboratively with experiment by Scott Anderson. I want to show you this beast because as I understand it's a heroic equipment that they've built. I cannot explain what's what, but bottom line was what they're doing for at least size selected cluster catalysis is that they must select the clusters of certain size. They're initially ionic, then they're soft landed on a support, and so you have a well-defined support with just one cluster size, well separated from each other, and then that is put into electrochemical cell under the liquid where they can do the reaction and spectroscopy also. Okay, so I'll show you this one study of this sort where we study HER, or the simple process where we produce hydrogen from H+ in solution. And it's catalyzed by platinum clusters, which are mass selected, and they're supported on fluorinated tin oxide, a typical conducting support that people use. And we see a couple of things that are interesting and interesting to understand from again fundamental theoretical point of view. First, we'll see high activity, much higher than polycrystalline platinum. Here, there's a comparison of platinum cluster sizes of 1, 4, 7, and 8 compared to platinum poly, what we call. And these are on two different supports, FTO and ITO, indium tin oxide, fluorinated tin oxide. You see, some cluster sizes really are much more active than platinum poly. And second, there's strong size dependence. Again, you see it from here, and you also see it from the current. So you see that platinum 1 is not particularly active, followed by platinum 4, and then 7 and 8 are more active, and they're close to each other. So we want to see if our model, however complicated, what I just described to you, can capture this effect, and then furthermore explain it. So first, this is busy slide, results of our modeling. First thing first, we need to see what's the state of the support in the reaction conditions. And what can happen is that it can undergo hydroxylation. So here I'm sampling the OH content on the surface. This is, you see there are fluorines, it's tin oxide with a little bit of fluorine. And it's a very abrupt change. So first there is just a couple, there are no protons, then there are just a couple, and they form like a water molecule, and then suddenly it undergoes essentially phase transition, where this water would give one of the protons to a nearby oxygen, and everybody becomes a hydroxyl. So it's a fully hydroxylated support as far as I'm concerned at relevant windows of the potential. This is going to be our support model. Then we sample our clusters on this support. So initially, without any hydrogen present, they have a couple of some structures accessible. GM stands for global minimum, LM1 stands for local minimum 1, so the second lowest energy isomer for platinum 7, for example. You see some differences in shape. And then we start sampling hydrogen coverage and placement on this cluster simultaneously with allowing the cluster to adjust its shape to hydrogen coverage. And what you see is that actually these clusters really like to uptake a ton of hydrogen, like at a coverage of about 3 per platinum, which is certainly not something that bulk platinum could do. At the same time, the cluster shape changes. I'm showing you just a few structures. In reality, my ensemble is much larger. It's hundreds of structures for which I don't have space on this slide. But you could look collectively at how hydrogen coverage changes as a function of the applied voltage for different cluster sizes. You see, as you go toward the negative voltage, you uptake more and more and more hydrogen. And simultaneously, cluster structure changes, as you could see from here, from RMSD as a function of coverage for the different platinum cluster sizes. Again, we have large divergence from the initial cluster shape as the coverage increases. So it acquires more and more hydrogen. Sometimes it goes to the point of platinum atoms going for a walk as a form of atomic hydride, and it can come back dynamically. So all of this can reorganize. And so, by the way, this hydrogen coverage also agrees with the experimental observations that could be derived from the experiment. How much there's a lot of hydrogen on this clusters compared to polycrystalline platinum. And of course, on platinum 1, you cannot do the same. Then we have an activity model. I will not go through details here. We basically build a model which allows to simulate reactivity on these clusters, encompassing the full complexity of the interface, where these clusters can change shape, but in such a way that the reaction network connects only neighboring hydrogen coverages. In other words, we can go from, say, 15 hydrogens on the cluster to 16, or from 16 to 17, but we would not go from 15 to 20 in one step. So in this way, we have a mildly connected network of these isomers that together create a model that reproduces, well, that aims to reproduce experimental observation in terms of activity. So we have this effective current in the end that we simulate from this network. And what I want to show you is a couple of things. So first, these are, you see platinum with hydrogen, and I'll remove the support for simplicity, but these are supported clusters. These numbers, H18, for example, is the coverage. And these are various isomers that are accessible. So vertically, we go they are all on the same footing. Okay, ground canonical free energies, all these isomers are compared. They have different structures and different hydrogen coverages. And then we connect neighboring coverages and create the model for reactivity in HER. What's interesting is that, again, multiple reaction pathways play a role, although not very many because we're in rather mild conditions, room temperature. Here, activity contribution from various pathways that we compute as a function of applied voltage. You see change players as you go toward a more negative voltage. Different cluster starts participating more and more compared to the initial conditions where, say, at close to 0, we have a variety of pathways contribute. And this is a simulated current, which I hope you agree agrees quite well with the experiment. So this model, with all this complexity, is able to now reproduce experimental observations for cluster size dependent electrochemical activity. Now you might think, okay, small clusters, of course, they're floppy, they're changing geometry very easily, fluxional, so on. It's not pertaining to bulk interfaces. We don't have to worry about it. I want to show you in the degree to which we have to worry about it when it's a bulk interface. So here we're looking at copper electrode studied by Beatrice Roldan in Fritz Haber Institute in Berlin. She is looking at the roughening of this electrode under CO2 reduction conditions. So initially, when the electrodes are prepared, they can be electropolished, they can be plasma treated in various ways. But if they're electropolished, they produce nothing but hydrogen. In other words, parasitic process of HR dominates. It cannot do CO2RR, whereas copper is known to be one of the best electrodes to do CO2RR. Then, after some time, the reaction apparently roughens the electrode. It creates active sites that are then capable of CO2 reduction. So our big goal in the program right now is to understand what is the nature of this roughening and where are the active sites. So to start more simply, and to also illustrate some of the issues of this bulk interfaces, I'll show you this. So we have copper 100 just put in the acidic conditions under negative voltage. From in situ STM, we see that initially we clearly see a nice lattice of copper 100. But as the voltage becomes more negative, we start developing these bright stripes, which become more frequent, and also the spaces between them become darker as the voltage goes to the negative. So clearly we have some severe reconstruction with the change of the unit cell. As a function of pH, we can, if the pH is higher, we start seeing blurrier stripes or no reconstruction at all eventually. But as a first shot, we would like to see, can our theoretical methods explain what this reconstruction is? So we sample these interfaces using our strategy that I showed you before. And here what we're looking at is a hydrogen coverage and free energy as a function of hydrogen coverage at 3 different voltages, at no volts first and then going to the negative. Every little dash corresponds to a structure that we sampled. So it's thousands of structures here really before we arrive to a conclusion of what might be the interface. At no volts, we have no hydrogen coverage. We know copper doesn't just take hydrogen. But as we go to the negative, we start forming a convex hole-like picture where high hydrogen coverage is actually favored. We could look at what the structures look like. And it's interesting because initially when there's uptake of these protons at the cathode, they walk everywhere. They don't really destroy interface in any way. They freely move. But at certain critical coverage of hydrogen, they all organize in a local hydride along a copper row that protrudes out of the surface, and I picture it in blue. As the hydrogen coverage increases, eventually there are more rows, and also space between the rows starts getting filled. And we simulate STM images for the structures, which I hope you agree are close to the experimental observations. So these structures are favored because this bonding motif for the hydrogen in this threefold site it's a very strong bond, which actually disrupts the bonding between the copper and the top monolayer and the monolayer below. So everything looks very cool, and we even can put this diagram, as a function of voltage. We have coverage dependent on voltage, and also structure of the electrode dependent on voltage, with one small problem that I'll expose now. In the experiment, all the shifts of the rows and jumps in the hydrogen coverage occur at much more negative voltage than my thermodynamic picture predicts. So clearly, we are failing somewhere with a thermodynamic-only view. And one place where we could suspect the problem is here. So we have a huge jump in hydrogen coverage in a very narrow window of the potential. So all these hydrogens, they come and go, they absorb, they move on the surface, they need to locally organize along this protruding row, which entropically probably is not very favorable. So something about the kinetics we're missing. Okay, so how can we go about it? We cannot possibly simulate all these events. We don't want to. We want to have phenomenological understanding. So we started playing with this model, more in a physics sense, I would say, if I'm allowed to say so. I'm a chemist, squarely. So we decide, okay, maybe this is just DFT. DFT, of course, is not perfect. We cannot put our foot on a number when it's special. It's Boltzmann statistics, and we put an error in exponential. So let's see. We have total energy as a function of hydrogen coverage here at different voltages. And if you really look carefully, you see bumps here. Maybe it's a bumpy surface because we have to create these protruding rows. So, okay, maybe these bumps are misrepresenting energy. Let's heat up the system. Let's throw some KTs at it. What would happen to this diagram? Of course, it starts shifting to the left. We're agreeing with the experiment better, but we're still not good with this first thing. So something is still missing. It's not just DFT, it's not just the kinetics in that sense. Okay. And then we said, okay, maybe it's entropic. And entropic in a sense that we'll never be able to grasp due to the complexity of all these different events present at the interface. So what we decided to say, okay, so entropy in what sense? Again, this organization of hydrogen is entropically unfavorable in principle, although enthalpically favorable. And second, reorganization of copper probably happens over some critical length scale that's beyond the length scale of my simulation, because I have just a small unit cell, 6 by 6. So we said, okay, may there be some entropic force that resists this reconstruction. We essentially effectively add a curvature to the surface through some fictitious force constant that's collective force constants for whatever entropic effects there might be. And of course, once we have a knob, we can shift the diagram closer to the experimental observations. But overall, as a chemist, I have a feeling that I throw my hands up because I no longer have the molecular level insight as to what's happening here. We just have a kinetic effect which we don't fully grasp, and it effectively represents the frontier in my mind of theory and electrochemical interfaces, which we're struggling right now. Okay, as a summary, catalytic interfaces can be extremely fluxional, even electrochemical interfaces. We can have radical change of structure of the interface that depends on temperature, chemical potentials of relevant adsorbates, and also the potential. The nature of the active site may change as a function of all these conditions and slight changes of voltage. We cannot assume one reaction profile. There can be many, and they should be viewed collectively. Less stable can be more active. I didn't show you this, but we break scaling relations. So if you're from catalysis community, this is some sort of holy grail there. Scaling relations break when you change structure very much. And also, in some cases, we really have to watch out for kinetic effects that break our convenient Boltzmann paradigm. With that, I'll close. This is my group, and part of it that's occupied with this heterogeneous catalytic interfaces. We do a million other things, including in biology, qubits, and so on. We burn a lot of computer resources, and I'm thankful to Air Force and Department of Energy and collaborators for helping me along the way. Thank you very much. I'll take your questions, Kaplan.
That was very nice. Major points that Alexandra is making is that you need to do the calculations at constant potential, and as the potential changes, you get reconstruction, which can dramatically affect the results, but it's not necessarily full equilibrium, and entropy plays a role. Do you have any comments or questions from the audience? Just yell out. Okay, there's only one?
In the last work where you showed the rows of hydrogen developing, was that at atmospheric pressure or at a lower pressure?
This is, well, it's atmospheric pressure, but the pressure doesn't come into the model specifically. What comes into the model is the pH in solution. That's what defines the chemical potential pressure.
Let me phrase the question differently then. When the hydrogen atoms come towards the surface, are they colliding with each other or touching each other, or is there a mean-free path where they're that is, why do they care about the negative potential on the metal? How do they experience that?
Okay, so this is electrostatics, the last part of your question, simple electrostatics, because we have a cathode and hydrogen is in the form of H+ in solution. In terms of path and collisions and so on, of course, these effects will play a role. This is more a transport question, which we don't address here. We simply look at the final result. What would be thermodynamically favored state of the surface once all these events have happened? So, and what you're asking actually is also very much related to kinetic effects, which we do not address. It's very complicated.
I see. Okay, thank you.
Yep.
More discussion from the audience here? Okay, wait a minute. Does anyone online have questions? Just unmic and yell out.
Yeah, I have a quick question for Anastassia. Simply a curiosity, do they have experimentally indications of a role of kinetics in the reconstruction of the copper surface, the row reconstruction?
it's all indirect. Like this, what I just showed you with this STM. I have to say that experiment sort of needs to catch up. We're at the point where we see things with theory that are like most of the observations in experiment, right? They're average techniques. They would be ensemble averaged observations. So these details of what exactly causes the signal is not something that experiment necessarily can detangle. And it's on the shoulders of theory then. Or there could be experiments that have a per site resolution. So if you could go with microscopy, FM or something like this. But then again, the likelihood of zooming on a particular majority site would be very high. And also, of course, it needs to be operando, which is very non-trivial. And all operando measurements, they're of course heroic and very admirable. So no, not directly. But if we have a disagreement with experiment, like with this copper story, then we have to suspect something. Yes. I think we're at the point where theory and experiment converge, and both need to develop.
All right. Let's thank Alexandra for a very stimulating talk.
Welcome.
We're going to now move on to the second